Hello everyone. Today we will solve another problem of PGT material, that is the piezoelectric material. So what is our problem? Like we have a piezoelectric material in which we applied a load, and due to the load, like we all know that the direct effect when you apply a load, strain will be there, right? So compute the stress required to produce a 100 microstrain in APC 856. This is the material name 800 APC 860. So we use all the properties of APC 850, right? So then we have to calculate the required stress to produce the 100 micron strain, and when the electric field is zero, this is our boundary condition. So when the electric field is held constant at zero, then only at that condition, boundary condition, we have to calculate the required stress to produce the 100 microstrain, right? And the second question is compute the stress required to produce 100 microstrain when the electric displacement is zero. So we have two boundary conditions, and we have two boundary conditions. In the first, when the electric field is zero, means E equal to zero, and the second boundary condition is the when the electric displacement is zero. So first we have to determine or know that what is the this condition and what is this condition, and what is the strain and stress relationship uh, when these two conditions happen, right? So let's see the conditions. So we have a piezoelectric material. This is wire and this is switch. So in the short circuit conditions, like first we applied the stress, right? First we applied the force F to produce the stress and strain. So and connect this piezoelectric material by the wires and a switch. So when you connect the switch, right, when the short circuit condition, so in the short circuit condition electric field is zero, right? Because the electricity, it flow the electricity, right? Current, if the current flow, then the zero electric field, right? Or this condition is called the short circuit condition. So in this is the like piezoelectric material matrix. This is a consecutive equation matrix. As the strain displacement equal to piezoelectric strain coefficient, uh, D compliance, dielectric permittivity, stress and electric field, right? So when electric field is zero, then S equal to ST, right? D equal to dt, because this is zero. Then you solve this, then you find that S equal to ST and D equal to dt. So like we use the short circuit condition, so we use superscript D, right? This is the superscript D, means this is showing or indicating that the electric field is zero. This is reverse. So this is showing that the electric field is zero. So this is our first condition when the electric field is zero. So we use this equation to determine the stress T. S is strain, this is capital S, this is small s. So this is the strain, this is the compliance. Compliance means, compliance is nothing but the 1 upon phi. This is the Young modulus, this is the reverse of Young modulus, right? So this is the compliance, and this is the stress equal to stress force by area. So this is the our first condition, and our second condition is the when the electric displacement is zero, right? So let's see the condition. So this is the reverse of this matrix. This is the for the direct effect, and this is for the converse effect, right? Converse effect means when you apply the uh, electric field, and the when you apply the electric field, then these conditions are measured. So this is the uh, inverse effect. So in the inverse effect, simply take out the inverse of this matrix. So this will multiply here. So this will become 1 upon s 1 minus 1 upon k square. K square is nothing but the coupling coefficient. Later on we will see that's what is k square. So when the condition is when the electric displacement is 0, capital D is 0. So when this is 0, then T equal to this multiply by this, because this will become 0, and E equal to this become this, this become this, because this become this is 0, right? So this is T equal to 1 upon S 1 minus k square multiply by S. By solving this matrix at the boundary conditions of electric displacement is 0. So like rearrange this. So then we found that strain is AC means electric displacement is 0. This is superscript. Previously we denoted by the SD, means electric field is 0, right? So AC 1 minus k square T. So this is our complete analysis of boundary conditions and strain stress relationship. S equal to SD T when short circuit condition, when you close the circuit electric field is 0, and AC 1 minus k square T when the open circuit means there will be the electric field but the electric displacement is 0, right? So we use these two conditions to solve a particular this particular question, right? So we have what is given, strain is given, or what is required, stress is required, strain is given, stress is required, and electric field and at the electric field and electric displacement boundary conditions. So let's see. So 100 micron stress is given, means S equal to capital S equal to 100 multiplied by microstrain means 10 to the power minus 6. Then we have APC 856 material. So these are the material properties, means piezoelectric strain coefficient, it's 612 picometer. What is compliance? Compliance is nothing but the reverse or 1 upon Young's modulus, right? Is 15 picometer, and piezoelectric strain coefficient is uh, 0.73, right? So first condition is short circuit condition. So we have to compute the T when the short circuit condition happen and this value of S. So this is condition. When you put here 100 micron, means 100 multiplied by 10 to the power 6, and this is value is given. So maybe this value can differ based on the material properties and which material you are using in your piezoelectric device or application. So these properties may change. So by solving this, we found that the stress comes out is 6.67 10 to the power 6 Newton per meter square. So this is the required stress to produce the 100 micro strain in the short circuit condition when the electric field is 0, right? And second question is this, that uh, stress required to produce a 100 microstrain when the electric displacement is 0. So this is our second condition. S equal to SE 1 minus k square T when the open circuit means the electric displacement is 0. So we have k value, we have S value, plugging these values in this formula, and we have strain value 100 micron. Then we can easily calculate T, right? uh, like divide this quantity by this, and we get 14.27 multiplied by 10 to the power 6 Newton per meter square. So this is the problem, and this is way that how we can establish the relationship between the strain and strain when these two boundary conditions. So this is the typical or very 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 important relationship between the stress T and strain S and compliance. So this is the very important relationship between stress and strain of a piezoelectric material when the two boundary conditions are given or when these boundary conditions are given. So this is question of the day, and later on we will solve more problems on the piezoelectric materials. Thank you.